This is a tutorial to post-process the data generated from the human random number generator exercise that we performed in class. The goal of this tutorial is to perform a Kolmogorov-Smirnov test, or KS test, to assess the goodness of fit from the data observed compared to an expected uniform distribution between 0 and 1. The data that we collected in class was provided in the human_RNG.csv file. This is a comma-delimited file that has 3 columns: the timestamp at which time the participant or the subject entered a random number value, the value that they entered into the text box on the Google form, and also a floating point number which measures the number of seconds that progressed inside of the minute that the entry was submitted at. So a value of 0.71, for example, is about 71% of the way between 0 seconds and 59 seconds. We're going to be post-processing this data to compute the necessary information required for the KS test, and then perform the KS test to assess whether the values and the times that these entries were submitted at adhere to or conform to a uniform 0-1 distribution. In this case, we're going to be using 3 packages to help with our analysis. First, going to import the numpy package and refer to it as np. Then I'm going to import the matplotlib.pyplot package and refer to it as plt. We'll use that for plotting. And finally, I'm going to import the scipy.stats package and refer to it as stats. That'll help us with some of our statistical analysis. Now, the first step of the script is to import the data from the CSV file. I already have it saved in the same directory as my script, so I can use the numpy.gen from text function, provide it the name of the file that the data is stored in, human_rng.csv, describe what the delimiter is. In this case, we use commas to separate the columns. And we want to skip the header on the first row to avoid reading in these header information up at the top. Now, the results of this gen from text function call I'm going to store in a variable data. So if I run this script, looks like I have a gen from txt, gen from text. If I run this script, then the data that gets produced is a list. It's a numpy array, a 2-dimensional array with these 3 columns. The first column is filled with nans, or not a number, because the original data has some strings or some non-numeric information in it. So from this raw data, we can first, we can also notice that there's some of these rows that have not a number data for the random number value that the participant submitted. I think in this case it corresponds to if they didn't submit any value, since this was not a required question in the Google form. So the first step to post-process this data is to remove those entries that have incorrect or incorrectly recorded results. So I'm going to override the data variable and perform a transformation using a numpy function. I'm going to generate a new numpy array. And the results of this array is going to iterate for over all of the rows and store the new copy of the row for each of the existing rows in the data, as long as the there isn't a nan entry in this first column. So we're going to store all of the rows. So we're going to store the list of rows for each row in the data, as long as we don't have, there's not numpy.isNan in row index 1. So again, what this is performing is building an array based on all of the rows for the rows in the data if the row index 1, which is this value column here, is not a nan, is not a number. So to rerun the script and inspect the data, you can now see that the value column only has data that are true numbers. So we've successfully post-processed the data a little bit. Next thing I'm going to do is simply extract out these two columns of interest, the value column and the time column. So I'm going to create a new variable, values, and pull out data, all of the rows and the first column, store that result in values. And what I actually will also do, so I can run this script, take a look at the values variable. We can see now we have a list of, just a list of records with one, it's just a one-dimensional list. What we'll want to do later on as well is to sort these observations in ascending order. And fortunately, NumPy has a nice function to sort data. So I'm just going to surround this extraction of column index 1 and perform the sorting operation. So now the values that we can observe out of our result are now sorted in ascending order with all of the 0 entries at the early portions of the array and then the large entries converging to 1 at the end of the array. So I'm going to perform this same function for the times. So the times are the sorted data, all of the rows, column index 2. So we can take a look at this times array. So we have, again, data ranging from 0 to 1. The other thing that we're interested in doing is computing a derived cumulative distribution function from this data. So right now, all we have are just these arrays of observations. But to transform it into a cumulative distribution function, we want to perform another kind of transformation operation on the data. So for each of these, for the values and the times, I'm going to create a new variable, values CDF. And we can use another type of a generator function similar to how we removed rows with a nan entry in a certain index to transform these raw observations into a cumulative distribution function. And what we really want to do is to think back, what is the definition of a cumulative distribution function? Well, it's a measure of how many observations are less than or equal to a certain observation. And representing that not in the counts or frequencies, but representing that as a fraction of all other observations. So we can represent that pretty literally using Python and NumPy. And what we want to do is, in the values case, is find the sum of the values that are less than or equal to some particular value that I'm just using a temporary variable x. We want to find the sum of all the values less than or equal to this x, divided by how many total values there are. So this case, I'm going to take the casting as a floating point number, the length of the values, which will tell us the total number of observations that are included in this values array. And actually, another shorthand for this, rather than casting as a float and using the default Python length function, we can also use the NumPy size function to determine what is the size of this values array. Okay, so we're finding the sum of the number of values that are, well, we're counting the number of values that are less than or equal to some temporary variable x, dividing that result by the total number of variables to get almost a probability, a fraction. And we want to repeat this calculation for each of the values in the values array, but we're just going to label each of those individual ones with this temporary variable x. So let's run this real quick. We can make sure that there's no syntax errors. This cumulative distribution function looks like it is not correctly casting the size as a floating point number. So I'm going to recast this as a float. Take a look at the values CDF. And now it is correctly ranging between 0 and 1, Although, since we have so many observations that are at zero value, we have a large number of, I guess we have a large block of results early on that say that 14.8 or 14.9% of the observations are less than or equal to the first value in the sorted array, which is really 0. Okay, let's do the same thing for the times. So the times CDF is the count of the times that are less than or equal to some time x, or t, sorry, x, and divide it by casting to a float the size of the times array and performing that calculation for each of the values x in the times array. Okay. So the times cumulative distribution function ranges between and roughly 0 and 1. And again, there's these discrete jumps because we only have a finite number of different observations for the times that these entries were submitted at. All right, so let's plot these data as we have them so far. I'm going to create a figure using matplotlib, and I'm going to use the histogram or hist function to plot the raw values and times and assign a couple of labels, values, times, and let's take a look at this. All right. Sorry, it's not labels, it's label. Okay, so there was a syntax error there. So here's a histogram showing the values and times. We can make it a little bit more clear by setting, for example, the X label is the bin, the Y label is the count, and let's add in a legend at the best location. Okay, so this is a bin of the random variables X. So as we saw in class, just based on the counts alone, there's a relatively large count of values at the extremes, and the times seem a little bit more uniformly distributed. We can also plot the expected result of the distribution. So I'm going to add in a plot ranging between 0 and 1. So this is just a straight line, so we can use 2 points for the x locations, 0 and 1. And what we expect to see is the uniform distribution PDF, which is 0.1. So the probability density function is 0.1 times the number of values that we have observed for each of these 2 points. And right. So there we can see the expected number of counts for this case would be, looks like about 25 in each of these cases. So let's run another plot. Instead of looking at the raw counts, display these cumulative distribution functions that we've just generated. So let's generate a new figure. And in this case, we want to create a step plot for the values and their cumulative distribution function for each of those values. So values CDF. Let's make this a blue line to match our previous plot and give it a label. This is the values CDF. And we'll create another step plot for the times and the CDF that would be expected. Let's make it green. Label as times CDF. And let's just add in some extra. X label is the random variable X. And in this case, the Y label is the cumulative distribution function, or the probability that X is less than or equal to some value, some particular value, little x. And we can actually change the x-axis to display little x. All right, so if we run the script with the cumulative distribution functions, we can see that they appear as these kind of discrete steps because we only have a certain number of observations at particular values. Let's add in a legend here so we can distinguish between these two cases. The values CDF seems to have a bias to be more likely for the low values than the times. Let's also overlay here the expected CDF from the uniform distribution. We know it's a straight line, but if we wanted to be a little bit more clear about the functional form, we could create a linear space, numpy.lin space between 0 and 1 for the x-coordinates of our expected continuous distribution. And our expected CDF is, the functional form is simply the x-coordinates between 0 and 1. So we can overlay this plot of the x-coordinates, the expected CDF, make it a red line, and a label of expected CDF. Okay, and it is indeed a straight line between 0 and 1. And we can see that our values CDF has a relatively large distance at a couple of points, where the times that the entries were submitted at does generally seem to follow this expected CDF line. So that those notions can be formalized. The degree of accuracy or fit for these two distributions can be formalized using the Kolmogorov-Smirnov test, or the KS test. So the next step that we want to do is to compute these test statistics. Now, it is possible to compute the test statistic by hand. So if you remember back to lecture, the test statistic is the largest vertical distance between our observed CDF values and our expected CDF. It's a little bit tricky in Python because it's a compound function, but I do want to walk through this function for you. The k-statistic value, the KS test statistic, can be computed, for example, for the values, and it is the distance. So I'm going to use the numpy subtract function. It's the distance between the CDF that was observed, which is again this blue line here, and the expected CDF. And we do have an equation for this, the expected CDF, where we have its evaluation at multiple points. But those points may not necessarily correspond to the points that we have the value CDF computed for. So rather than using that expected CDF in the subtraction, what we want to do is to build a new expected CDF based on the particular value locations that we do have identified from our observations. So we're going to create a new function. And if we think back to the functional form of the expected CDF, it's simply the x locations that each of the observations were created. So in this case, it is the values. So it's the x locations for each of these value observations is the values themselves. And that is the expected CDF. So we want to subtract these two components, and then we want to take the absolute value of that computation, and finally find the maximum absolute value of that range. So if I run this script and take a look at the k test statistic for values, it returns a result of about 0.18, which does indeed look right around in this range. It looks like the maximum distance between the blue line and the red line appears to be about 0.18 or almost 0.2 distance units. So again, just to walk through this computation again, we have the values CDF, which is this list of the cumulative distribution function that we had previously computed. The actual values that were observed are in this values array. And if this did indeed follow the expected cumulative distribution function, our expected CDF value for each of these x locations is the x location itself, because for a uniform distribution, the CDF equation just follows this linear relationship. And if we take the subtraction of these two, we get the difference between our computed CDF and our expected CDF. And then we take the absolute value of these numbers to remove the negative symbols. And finally, the maximum of all of these entries is computed with the max function, which returns 0.18. So we could do the same thing for the k-test statistic for the times. It's the maximum of the absolute value of the subtraction of the cumulative distribution function we computed for times and the times themselves, which is how we would expect the CDF to be arranged. So if we run run the script again, the k-test statistic for the times is much smaller. It's 0.04. So it's probably in one of these regions here where our computed CDF seems to be larger than our expected CDF value. All right, so this is, you can compute the k-test statistic by hand. However, if you want to perform a goodness of fit test, you'll need to compute a critical test statistic value. However, in many cases, it's much easier just to use a statistical library function to run this test. And in particular, the stats package has a test, ks test. We can take a look at using the object inspector, Control-I, some of its arguments. It requires the random variables that were observed, and then actually a function to express the CDF or the expected CDF for these data. The rest of the parameters are optional, and it returns two values, the test statistic and then the p-value or significance level of the result. So in this case, for our values, for example, are the random observations that we've observed or values. And the CDF that we've observed or the CDF that we anticipate is this linear relationship that we would expect from a uniformly distributed random variable. However, to express this as a function, we can use kind of a nice trick in Python called a lambda function. A lambda function is a very shorthand to represent a function in one little block of code. So what this lambda function expresses, for example, is that there's a function with one argument or one parameter x, and the return value of this function is x itself. So just as a quick demonstration of this, I could have my expected CDF as a lambda function is lambda x, and then return x. And then if I were to use this expected CDF lambda, passing in the value 0.5, it returns 0.5. If I pass in 0.25, it returns 0.25. This is essentially a nice shorthand to express a functional form without having to discretize the function over many values, like what we've had to do in the past for plotting. So this KS test is comparing the values we observed with the expected CDF function, which is big F of x equals x. And we can store the results in this as a k values 1 and then a p values 1. All right. Run this test, k values 1. The result, oops, forgot a comma here. K values 1 is this result that we had computed earlier. It's about 0.81 or 0.18. And our p values for the significance level for our goodness of fit test for the values test is a very small number. It's 1 times 10 to the negative 7th. What this means is there's a high degree of confidence that we can reject our null hypothesis that the values data comes from the same distribution as expected. And we can clearly say in this case that the two come from different distributions. However, if we run the statistical test for the times data, and I'll just copy and paste and change the name of these variables. We want to use the same expected cumulative distribution function. The k times data, again, this returns the largest vertical distance between our observed CDF and our expected CDF. And our p-value for this test is 0.75. This result means that the results are not very significant towards the null hypothesis, meaning we cannot reject the null hypothesis. And it is likely, in this case, that the time that the participants submitted their data does indeed follow a uniform 0-1 distribution. Now, this goodness of fit test doesn't check other features that we would desire from a random number generator. For example, having the samples be independent of one another. We did show in lecture that these times that the variables were submitted at appear to be correlated with each other. However, we would need to test